Hi, welcome to Chapter 8 and 9, Chemical Bonding, Overview Part 1, where we're going to discuss Lewis symbols and the octet rule, ionic bonding, and covalent bonding. So let's start with chemical bonds. What are the different types of bonds, and what defines these bond types? Well, there are three basic types of bonds. Ionic, which is normally, we classify it as a bond between a metal and a nonmetal. And what holds them together is the electrostatic attraction between the ions. Here you have a transfer of electrons. The second type is covalent, where you have two or more nonmetals, and here you have sharing of your electrons. And the third type is metallic, where you have two or more metals, and here you have free electrons that hold the metal atoms together. So we like to say a sea of electrons. So you have your, let's take silver, you have your positive silver, and then you have your electrons kind of floating around in your sea of electrons. So let's talk about Lewis symbols. Hopefully you remember this from your first year of chemistry. This symbol is the same symbol as the periodic table, and that is all of your core electrons. And then you just put a dot for your valence electrons. So the dot equal your valence electrons. So if you're in group 1, you have one valence electron. So you see here, like sodium, you have one dot on there. Okay. So for your core groups on the periodic table, groups 1, 2, 3, 4, 5, 6, 7, and 8A, the dots range from 1 all the way up to 8 for the noble gases. So here you'll have 8 dots. Here you have 1 dot. Okay, and what kind of helps us determine this is there's something called the octet rule. Octet meaning 8, right? So when we're forming compounds, your atom either tends to gain, lose, or share enough electrons so that you get 8 valence electrons surrounding it. And that's the octet rule. So let's talk more in-depthly about ionic bonding. Again, it's between metals and nonmetals, except your noble gases. They don't really form ionic bonds. You have an electron being transferred, and the formation of this bond is very exothermic. It releases a lot of energy when ionic substances are formed. So you'll have one element that is giving up the electron, and that's normally your metal. And they have a low ionization energy, so it's easy for the electron to be removed. Then you have another element that gains the electron, that's your nonmetal. And they have a high electron affinity. That is the energy released when it gains an electron. So you see here, sodium is going to give up its electron. It has a low ionization energy. Chlorine accepts the electron. It has a high electron affinity. And then you're going to form your cation and your anion. Notice your cation has no dots around it because now you got rid of the valence electrons, but chlorine has 7 dots. You put brackets around it and then the charge. Okay? When sodium chloride is made, it is highly exothermic, So what are some properties of ionic substances? Well, you get a well-defined 3D structure, a crystal, which are brittle. They have high melting points. They form crystal structures. You could actually cleave them along smooth lines. What does cleave mean? Cut them. You could kind of chop it along a smooth line. And the smooth lines that you could cleave it on are called cleavage planes. But what holds an ionic bond together? Well, it's the attraction of the ions that you form that actually holds the bond together. And it can be described by Coulomb's force here, which F is the force, K is a constant, Q1 is a charge on one of the ions, Q2 is the charge on the other ion, and R squared is the distance between the ions. So the larger the charges, the larger your Q's, the greater your force of attraction. And the smaller the distance between your ions, the greater the force of attraction. So let's talk about the energy that's involved in making an ionic bond. So last chapter we saw that when you remove an electron from a metal, you have to put energy in, and that energy is called ionization energy. Since you're putting energy in to remove the electron, it is positive. So in this case, for sodium to become Na+, you have to add 495 kilojoules per mole. And then we saw when an atom accepts an electron, that's called electron affinity. And in most cases, when it accepts an electron, it releases energy. That's why this is negative. So what value for the change in energy would you expect for a reaction with sodium and chlorine? Well, you would kind of expect that you take the energy you have to put in to remove the electron from sodium and then combine it with the energy that's released when chlorine takes that electron in, and you would get 146 kilojoules per mole. But this is not the energy of the ionic bond, okay? These numbers do not explain why the reaction between sodium metal and chlorine gas, when they form sodium chloride, is extremely exothermic. Extremely. If it's extremely exothermic, it would be negative. This number is a small positive. So there's something else going on here. So there must be a third piece of the puzzle, and we've already kind of mentioned it. It's the attraction between the ions. So here, it's we haven't really gone in depthly talked about it, but the electrostatic attraction between the sodium ion and the chlorine ion. This attraction we call the lattice energy, okay? And the lattice energy is the energy required to completely separate a mole of a solid ionic compound into its gaseous ions. So if I had 1 mole of sodium chloride and I separated it into its gaseous ions, the energy I have to put in to do this is called your lattice energy. So, and this is related to the electrostatic interactions governed by Coulomb's law, where Q1 and Q2 are your charges and D is the distance between your ions. So let's talk a little bit more about lattice energy. Again, in your textbook, they define lattice energy as the amount of energy you need to separate 1 mole of a solid ionic compound into its gaseous ions. So if you are separating your compound into its ions, you have to add energy to do that. So that is why your lattice energy in this case is positive. It's endothermic. But I have been reading up on lattice energy, and in some other places, it seems to be more commonly referred to as the amount of energy to make a solid ionic compound. So if you are making a compound, you have your sodium ion plus your chlorine ion coming together to form sodium chloride. In this case, you're going to release energy. So it is exothermic and negative. And this negative lattice energy here is also the amount of energy that's released when we make ionic compounds in a Born-Haber cycle that we're going to talk about in a few slides. Okay, so the magnitude of your number is the same. The sign just changes. So if you are breaking apart, you have a positive sign. So you have to put energy in to break apart things. If you are forming, then it is a negative sign because energy is released when you form. So let's look at this table of lattice energies that I got out of your book. Notice all these are positive. Since all these values are positive, Is this the lattice energy to form an ionic compound or to break them apart? Well, let's think about it for a minute. If we are forming, we release energy. If we're breaking apart, we have to put energy in. So this is for breaking apart. So let's take this one up here, for example. So that is positive to break it apart. You have to put energy in to break it apart. So what are some trends in lattice energy? Well, two things control your lattice energy. The amount of charge on your ions. So if you have an increasing amount of charge, you're going to get a higher lattice energy. The other thing is the size of your ions. If you have smaller ions, the distance between the ions will be smaller and you will have a higher lattice energy. So because lattice energy decreases as the distance between the ions increases, lattice energy follows trends parallel to those with ionic radius. So let's look here. You see here, we're going from lithium chloride, sodium chloride. And if we look at the periodic table, it goes from lithium to sodium, to chlorine, to rubidium, to cesium. Let me clean that up a little. So as we go down a group, our radius gets larger, right? And what is happening to our ion is our lattice energy here. Since the radius gets larger, the lattice energy decreases. And you can see the same thing here. In this case, we're just changing the anion. I guess I should make these ions. Again, as we go down, we're getting larger. The radius is getting larger, so the lattice energy decreases. So again, lattice energy is affected by the size of your ions and the charge. So the lattice energy will increase when the charge on the ion increases, okay? It will also increase when you decrease the size of the ion. So the last slide we talked about this, decreasing the size. So now let's look here. And let's compare some compounds where the charge is changing, okay? So here we have lithium chloride, which is +1 and a -1. And here we have magnesium chloride. So the chlorine is the same. The only thing that changed is that now we have magnesium, which has a +2. So what do you notice about the lattice energy here? It increases, right? So as the charge increases, lattice energy increases. And then look here. Here we have a +2 for magnesium and a -2 for oxygen, and it increases even more. So which factor has the greatest effect? Charge. So changing the charge will have a greater effect. So let's see if we could pick which one of these has the greater lattice energy. So let's look at the first one, barium fluoride and calcium fluoride. So as we go down, our radius gets larger, so the distance will increase, so the attraction will decrease. So calcium fluoride will have the larger lattice energy because it has a smaller distance between the ions. Okay, so now let's do the next one in another color. We have sodium chloride cesium bromide, and rubidium bromide. So let's compare these two first. Cesium and rubidium. Cesium is lower down, so it will have the lower lattice energy. So rubidium is higher than cesium bromide. But let's look at sodium chloride. Sodium chloride, each of these, if you look at sodium chloride, so this is Na plus, Cl minus. So your Na plus here will end in a 2p6, and your Cl minus will end in a 3p6. And if we look at our rubidium plus, Br minus, rubidium plus will end in a 4p6, and bromine will end in a 4p6. So sodium chloride will have the highest because it has a smaller distance between the ions. Now let's look at barium oxide and Kf. So barium oxide has more charge, so it will have a higher lattice energy. Okay? Higher charge. So now the last example, you have magnesium oxide, which is +2 - 2, lithium fluoride +1 - 1, cesium iodide +1 - 1, +2 - 2. So you know the +1s are going to be smaller, so we could just get rid of them. Now let's compare. Let me erase all these circles here. Let's compare magnesium oxide and strontium sulfide. So magnesium oxide and strontium sulfide. And let's look at their electron configuration. So this is Mg +2, O -2. So Mg +2 will end in a 2p6. Oxygen -2 will end in a 2p6. Strontium sulfide, strontium will end in a 4p6, and sulfur will end in a 3p6. So magnesium oxide will have the shortest distance because it's the smallest ions. Okay. So let's talk a little bit more about the energies involved in ionic bonding. So why do we never see an Na2+ or a chlorine 2- in an ionic compound if the enthalpy of the lattice formation is so highly exothermic? Well, as it turns out, metals tend to stop losing electrons once they attain the noble gas configuration, because the energy that would be required to remove an electron from a lower energy level would be just too great, and it cannot be overcome by the lattice energies. So that's why you see a Na+ or a Cl-. But on the other hand, why are we able to have an iron 2+ or an iron 3+? Well, main group metals lose electrons, and they result in the electron configuration of the previous noble gases. Nonmetals will gain electrons to get to the noble gas configuration. Transition metals do not follow the octet rule. Transition metals lose the valence electrons first, then they will lose their d electrons. So let's look at iron's electron configuration. And let's see what happens when we form iron 2+. We are going to lose the electrons from the 4s first. See, notice the 4s is no longer in here. And now if we want to form iron 3+, we could start losing electrons from the 3D. Okay. So we've been talking all about this lattice energy, but there is no easy way to measure it. But luckily we could calculate it, sort of like when we did Hess's calculations. You could use various paths, add up all the energies to figure out what the lattice energy of an ionic compound is. So there's many factors that affect ionic bonding. So the first thing we're going to always start with is the enthalpy of formation of our compound. So that is when you take elements in their standard state to form 1 mole of the compound. So you have solid sodium plus gaseous chlorine, half of that equals NaCl solid. And that is your heat of formation. So you see here, your heat of formation is pointing down because most of the time it's exothermic. Okay? Next, we need to make gaseous atoms. So we need to convert our solid sodium into a gas. And this has many names. It's called the enthalpy of atomization or sublimation. You might see that also. Okay, so in this case here, this is endothermic. You have to add heat in to turn your solid to a gas. And that is represented right here. You see, you're going from a solid to a gas. So this arrow here is your enthalpy of atomization from solid sodium to gas sodium. Then you have to do the same thing for your chlorine, because chlorine's a diatomic. You have to break that bond and make it a single gas atom. So you have to add energy for that, and that is what's going on here. You see, you're taking your chlorine diatomic, converting it to just a single atom. Next, you have to make your atoms into ions. So for sodium to become an ion, it has to lose an electron. When we lose an electron, that is called ionization energy. So here is our ionization energy to take a gas of sodium and turn it into a sodium ion. That's a gas. So this is your ionization energy. And remember, ionization energy is the energy you're putting in, so it's positive. Then we have to take our chlorine gas and turn it into an anion. So it takes an electron in, and it becomes a negative ion. This is called electron affinity. And this is, for the most part, negative. So you see the arrow pointing down. That's to change chlorine gas to chloride gas. Then when you combine your two ions together, you get your sodium chloride, and that is your lattice energy, which is this last bit here. Now notice it has the arrow going down or up. It depends on how you're defining your lattice energy. If you are defining it, in this case where you're making the solid, then this would be negative. Okay? So by kind of adding up all these energies, you could calculate your lattice energy. So what's involved in the ionic bonding? Well, we already discussed that you have to make them ions when you have ionic bonding. So you need to know the ionization energy and your electron affinity. You need to know the energy it takes to convert an element to the atoms, and that is you're adding energy in. Then the energy it takes to create the cation, right? And that is your ionization energy. The energy released when you make an anion, that is your electron affinity. The formation of a solid from the two ions coming together, that's your lattice energy, and that is hugely exothermic. When they're coming together to form the compound. So as a result, since this is so huge, it kind of dominates all of this. When you form an ionic compound or a salt from the elements, it is hugely exothermic. So we've been spending all this time talking about ionic bonding. Let's introduce covalent bonding a little bit. In covalent bonding, atoms are sharing their electrons. There are several types of electrostatic interactions in these bonds also. You have the attraction between the electron and the nuclei within the atom. You have the repulsions between the electrons between two atoms. And you have the repulsion between the nuclei between two atoms. I should go back here. It is within the atom, and you have attractions between the two atoms. So here we have hydrogen single bond. Okay, each hydrogen has one electron. Right, so here's our Lewis dot for that. As they come close to each other, the electron from this atom is going to be attracted to the nucleus. So maybe I'll draw. That's a terrible drawing. Let me erase it. So each hydrogen has one proton and one electron. As they get closer to each other, the electron from this atom is going to be attracted to the proton of this atom. And the electron from this atom is going to be attracted to the proton of this atom. But when these get close together, these two electrons are going to repel each other. And then if you get too close together, this proton will repel this proton. So because of that, there is an ideal distance between these two, and that gives you your bond length. So a bond forms because the attraction must be greater than the repulsions. So here's a density diagram here, and you see here, there's a concentration of electron density between the nuclei and the covalent bond. So here you have a concentration of the electron density. And so these electrons are attracted to either one of the nuclei. So here's a diagram of a formation of the single bond between hydrogen. At which point in the graph is the hydrogen molecule most stable? That would be right here, the lowest point, the lowest energy. Most stable. What is the average bond length of hydrogen? Well, that would be 0.74 angstroms right here. What happens to the stability as the bond length decreases? So if I tried to push my atom closer together, what happens to the stability here? It becomes unstable. Why is it becoming unstable? As these two start getting close to each other, the two protons, the protons in the nucleus of each atom repel each other. And the electrons are going to repel each other too. What happens to the stability of the bond as the length increases? It becomes unstable. How do you know this? Because from the energy graph, you see the energy is increasing. And why does the stability decrease? Because as you get further apart, the electron from the opposite atom no longer feels attracted to the nucleus of the opposite atom. Remember, your force of attraction is related to the distance. You're just too far away. You're so far apart that the electron that's sitting here and the electron that's sitting here that used to be attracted to this nucleus and this nucleus, they're just so far apart they're not really feeling the attraction anymore. Okay, and that is the end of part 1.